Hello, AP Chemistry students. This is section 3.4, an addendum on the combined gas law. So this is an equation that is not explicitly in the course and exam description for AP Chemistry, but I thought would be useful to learn. And also, we're going to be using it for a lab assignment this week. And it's pretty simple. So the combined gas law is an equation that relates the pressure, volume, and temperature of a gas under two sets of conditions. So you have your initial conditions that are represented as P1, V1, and T1, and then your final conditions, which are represented as P2, V2, and T2. And this is useful if your conditions are changing and you know how two of the variables change and you want to predict how the third variable is going to change. So say, for example, your temperature is increasing and your pressure is increasing, you can then solve for the change in the volume. This is also related to what we were talking about last time about how pressure and volume are inversely related. So if the pressure is going to go up, the volume is likely going to go down as a result, and vice versa. And then how pressure and volume are directly related to temperature. So if the temperature is going to go up, we can predict that the pressure and the volume are going to go up as well. So let's do a practice. So say we have a gas at 2 atmospheres. It's contained within a rigid volume of 1 liter and has a temperature of 30 degrees Celsius. What will the new pressure be if the temperature rises to 60 degrees Celsius? So if you look at this first sentence, we have our P1, we have our V1, and we have our T1. And then the pressure is going to change. We don't know what the new pressure is going to be, so we're going to be solving for P2. And then we have our T2 here. You'll notice that there's no V2, but if we look at this first sentence, it says we have a rigid volume. That means that the volume of the container is not going to change. So that means that the V1 is going to be equal to the V2. Also, this might look like the temperature is doubling, but remember in chemistry, when we're talking about temperature, we want to think about things in terms of an absolute scale. We don't want any zeros or negatives, or else our math is not going to make sense. So we're going to want to convert both of these to Kelvin. So let's solve. So I like to always solve this symbolically first. So we want to know what P2 is. So I'm going to rearrange the equation to get P2 over here. And P2 is going to be equal to P1 V1 T2 over V1 V2. So then I can plug things in. We have 2 atmospheres for our initial pressure, 1 liter for our initial volume. It's kind of hard to see here, but this is 333.15 degrees Kelvin for our final temperature. Then divided by our initial temperature, which is 303.15 Kelvin. And then our final volume is 1 liter because the volume did not change. So those instantly get canceled out. So then I do 2 times 333.15 divided by 303.15. Kelvin cancels out, and then I get left with units of atmospheres. That'll be 2.2 atmospheres. And this makes a lot of sense considering that there's a direct relationship between pressure and temperature. The temperature increased, the volume stayed the same, and we could predict that the pressure would increase as well, and it does. So let's do another one. The pressure of a flexible 2-liter container of gas is 740 millimeters of mercury at 20 degrees Celsius. What will the volume of the container be at STP, standard temperature and pressure? If y'all recall, standard temperature and pressure is equal to 0 degrees Celsius or 273.15 Kelvin and 1 atmosphere. Since this problem is in millimeters of mercury for pressure, it doesn't matter what pressure units you use as long as your P1 and your P2 are the same. We're going to want to figure out what STP is for millimeters of mercury. And if we recall, 1 atmosphere is equal to 760 millimeters of mercury. So that's what we're going to use as our P2. So let's start solving. So we're trying to figure out what the volume of the container is going to be under these new conditions. So we're solving for V2. And using algebra, we get P1 V1 T2 over T1 P2. Then we can plug everything in. So our initial pressure was 740 millimeters of mercury. Our initial volume was 2 liters. And we have a flexible container this time, so the volume will change. Imagine the gas is contained within a balloon or something like that. We have our T2, which is our 0 degrees Celsius slash 273.15 Kelvin. And then our initial temperature, which was 20 degrees Celsius, aka 293.15 Kelvin, and then divided by P2, which was 760 millimeters of mercury. You can see here millimeters of mercury cancel out, Kelvin cancels out, and we get units of liters, and we end up with 1.81 liters. This makes a lot of sense because the pressure and the temperature are going down, which likely means that the volume is going to decrease a little bit as a result. So that's the combined gas law, and I'll see you in 3.5.